Thank you, Victor, for the lovely introduction. So hi, as Victor mentioned, my name is Nikhil, and I'm going to be talking about modeling and verification of distributed systems. Now, I'm going to be actually specifically talking about some formal methods that you can use to verify systems. I've tried to make the talk oriented towards distributed systems, but a lot of what I'm actually going to be talking about can be actually verified, can be used for like any system. So examples that I have picked are specifically around distributed systems, but you can have, you could use the same techniques for like embedded system, for example. So it's not going to be restricted to distributed system. Now, specifically, I have two objectives. So my first objective is, and I'll explain why with some demo and examples, that you need to test your design. And I'll expand on what I mean by design in a short while. And the second objective that I have is, why should you test your design with formal methods like TLA+? I'm going to be talking mostly about TLA+, although I do include a little bit of information about other formal languages and kind of draw comparison about them. Like in the given span of 40 minutes, obviously formal method is actually going to be a very big topic. I can't cover all of it. So specifically, I'm more interested in why you should test your design, right? How to get started and what are the kind of problems you can use to solve. So let's look at a typical software development process, right? Very, very typical. You have a problem, you come up with a design, some algorithm, whatever you have, whether you write it on a piece of paper or not, that's immaterial. You implement it and then you test it, right? Pretty simple. And you can do it in cycles, or what we call as agile, in sprints of 2 weeks, or you can do it in waterfall, do all the algorithm design in one step, and whatever development methodology you use, but essentially you're doing this step. And the problem is that while you test your implementation, we don't test our design. So when you look at bugs or faults or whatever you call it, there are two categories of bugs, right? One, you have your design, you implemented it, but your implementation does not match the design that you have, and because there are bugs, and that's what you do by testing. But there is another category of bugs which is often overlooked, and that is there's fundamentally something wrong with your design, especially in concurrent systems where you can have bizarre race conditions and so on. So fundamentally there is something wrong with the design itself. So your implementation is correct or it matches the design, but your design itself has a problem that you realize when your code runs in the production. And at that point you basically have to do an expensive rewrite. So that's the reason why you should test your design, right? The thing is that human mind is limited in thinking about next steps at a scale. A good example is I play a lot of chess. So when I play chess, I can think 3 or 4 moves ahead of me, right? So what my opponent is going to do, great, 3 or 4. Years ago, and this was like 20 years ago, Gary Kasparov, the greatest chess player ever, played against that machine called Deep Blue supercomputer, and lost. And I'm sure Gary Kasparov is probably 100 times smarter or better than me in chess. So maybe he can analyze 300 or 400 moves ahead. I don't even think he can do that, but let's assume he can. But the computer he was playing with could analyze 1,000,000 moves ahead, right? So he lost, and that's the problem with human mind. You can think about these problems at a small scale, but when you're reading your production code, right, you have 1,000 plus microservices or whatever with multi-threading, multiple threads running, bizarre kind of conditions happen that it is simply not possible for us humans to really think about everything that can go wrong. And that's the reason why we need to test these design. So, when you go typical, software engineering interviews, they ask you to do all these on a blackboard, invert a binary tree, sort a linked list, whatever. And you have these edge and border conditions, right? And a good 50% of people fail in those interviews, probably more, because they did not think about all the edge and border cases. And that's like what, 30, 40, 50 lines of code, right? That's what those problems are. And in production we have 10,000 lines of code. So if we can't think about all the edge and border conditions, or at least half of the people can't think about all the edge and border conditions in a 50-line code, you really think you have a better luck thinking about it in 10,000 lines of code? Good luck with that. So the question is, now that we know that we need to test the design. The question is, how do you do it? Well, you express your design in some kind of formal languages, and we'll see some examples of it. So some kind of formal languages which can be verified. And I'm specifically using the formal languages because informal languages like plain English, it leaves a lot of ambiguity in it. So you don't want that ambiguity. And then what you do is you check for conditions like, specifically since I'm talking about concurrent system, these are things that can go wrong, but in general, a lot of things can go wrong, right? All the edge and border conditions. So you check for these conditions. So use formal methods. But what do you get? Simple, you get a very good understanding of your system, right? It is the way human mind works, right? I have an idea, it's good, but when I write it on a piece of paper, even if that document is for somebody else, when I write that idea on a piece of paper, above everything else, it helps me, it clarifies my thinking. Even though it is intended to clarify the other person's thinking, but your own thinking gets clear. So when you basically use a formal language to express your design, you get a very good understanding. A lot of times while you're modeling, you will figure out that something is wrong, even before you write a line of code, right? So a model of an algorithm will not contain all the mundane, unnecessary details, right? It's a high-level model. And these models can be verified mathematically, and I have a demo in which I'll show you how you can do that. And of course, you get bragging rights. So you get to impress other people, like, look at this cool new funky set theory that I've applied on my system, and look. And people, even if they don't understand, would think you're really cool about that. Anyway, so let's talk about formal methods. Now, there are a whole bunch of formal methods that exist, and I would see these formal methods as a spectrum. With one end, they're a little bit more mathematical and theoretical, probably more useful to academics, and on the other hand, I have this practical or implementation-oriented methods. So, interactive proof systems, COC, ACT-Isable. I've used COC a while ago when I was a student in France. So that's somewhere in the middle. And then you have specification languages, TLA+, which is what I'm going to be talking about mostly. Z, which was probably Alloy, which came out of MIT from Daniel Jackson's research team, which uses satisfy solver. So that's more implementation oriented. And then you have automated theorem proving and SPAS, which for the purpose of this talk we would not talk about because they are mostly useful for academic research. So we'll talk about TLA+, but mind you, TLA+ is only one of the many options that you have. So temporal logic of actions, that's what it's called, formal specification languages. And it uses, basically it's a state machine, and when I give the demo and go into details, it'll become clear. It's basically a state machine that examines all the states, which is basically examining all the edge and corner cases of your system to make sure certain properties are verified. And you'll have some invariants, you'll have some temporal properties. Temporal properties are properties that are eventually going to be satisfied. So in distributed systems, you have this concept of eventual consistency, right? A certain condition eventually, and eventually could mean couple of seconds, eventually will be true, but it may not be true at every step while the process is going on. So you can have these specifications in TLS model checked, and I'll give links for a model checker in demo also. I'm kind of using it. So a little bit about history of TLA+. I don't want to spend too much of time in the history, but it was done by Leslie Lamport, who has a lot of inventions. LaTeX is probably his most famous one. I love LaTeX. I'm sure everybody at least knows what it is. And obviously he got a lot of awards, including Turing Awards, which is like the Nobel Prize of Computer Science. If you were to put it this way, that's him, and that information you can see on his Wikipedia page. So really smart guy with lot of accomplishments. He was the one who came up with TLA+. And now, before I go into details of TLA+, like I said, I actually want to compare how TLA+ compares itself to other formal languages. So there are advantages, obviously, of TLA+, that it was designed specifically for software engineering problems. So it was not, although in my personal opinion, the syntax is very mathematical, but that's my personal opinion, but essentially it was designed for software engineering problem, mostly about concurrency and and distributed systems. So certain things like, it has certain construct, and we'll look into those constructs later on that kind of model eventual consistencies or basically partial failures. Relatively, and I'm using the word relatively, mind you, less maths required. And it can work at multiple abstractions layer. The syntax will become more clear when I show an example. Obviously, it has certain disadvantages, so I want to prevent like both sides of the story. The proof system is not very intuitive. Even the syntax is actually a little bit weird, personally. Model checking is very low because you are examining all possible states. So when you examine all possible states, you obviously go into state space explosions. However, there are ways in which you can basically control the state space explosions, and I'll talk about that also towards the end. And because it's relatively new, there is less academic literature available compared to other alternatives. So these are like the disadvantages. So how does TLA plus work? The way it works is that this is a sample code, right? It gets translated into kind of a state machine. And TLA model checker will basically do a bunch of stuff, like it'll treat the state machine and runs them through step by step. It runs them in parallel because it has to model multiple threads running. It basically explores the transition by all possible states. So this is where all the border and edge cases that I'm talking about, that's done. There are non-deterministic behavior combinations. I'll cover that also. And it checks all the temporal properties. So I briefly mentioned temporal properties, but think of them as eventual consistencies. Assertions is something that is going to be true at that point of time, and invariant is something that is true at every point of time. So that's the difference between assertion, temporal properties, and invariants. So there's a big ecosystem here, right? Original TLA plus, which had a very weird syntax, was basically a bunch of mathematical expressions, and then it was refined as Pascal, which is basically a general programming language kind of syntax. And what happens is that you can write TLA plus itself, but people will use Pascal. And I'll have references towards the end where Amazon and all these companies, and they have used TLA plus, and they even have some of the implementations that actually are public. So you basically transpile it into TLA plus. And this is the TLA proof system. So there's a proof system, there's a toolbox, and there are command line tools. That's the one I'm actually going to be using for the demo. I love the command line stuff. I know I'm a little bit old-fashioned that way. And then you have various plugins for Visual Studio Code, Eclipse, and so on. So I'll just maybe stop here and open up my browser. So this is the TLA plus proof system. This is where the toolbox is, and in demo that I have, I'll be basically running these command line commands basically. So next. So before I go into the details, I actually wanted to bring the demo in the middle, because so that way it kind of gives you a taste of what it is. I've put the demo publicly, so you can actually go to my GitHub, and the demo is public. But so the problem statement is that imagine you're building a financial system, right? So you're building a financial system, and what you want to do is you want to transfer money. Okay, you want to wire money. And how do you wire the money? You have two entities, two customers, and you spend X amount of dollars or euros, whatever currency you're dealing with, from customer 1 to customer 2, right? With certain set of conditions like, customer 1 should have the required balance in his account. So if I'm giving you $100, I should at least have $100 in my account. And these can be long-running transactions. So they are not like, it can take a while, especially if you're dealing with international transactions. So the problem statement is that we have two customers, Jack and Jill. And what we want to do is they have initial $100 in their account, and Jack is going to transfer $65 to Jill, and then also Jack will again transfer $50 to Jill. Now ideally, the second transaction should not happen, because once $65 is done, Jack has $35 left in his account, so second transaction should ideally fail. Now here, obviously because we want the system to be scalable, so we have all of this wrapped up in a thread. So if I was to design such a system, I will come up with an algorithm, right? Something like this, simple, that if the sender has more money than the amount I'm transferring, then just deduct that much money from the sender and add that much money to the receiver. Otherwise, just throw an error or exception or whatever you want to do. And because this is a multi-threaded system, and these operations should be thread safe. It's kind of a very simple problem, right? Of course, it's not that simple, but it looks simple. It looks deceptively simple. So now let's actually look at the implementation. So this is the implementation. I have a bunch of mutexes, right? And I have these transactions are done in threads. So I start these threads, I stop these threads, and at the end, I just print the balance. Now, what I'm expecting is the first transaction should go through and second transaction should not go through, because this error should come, right? So I'm doing this check. If the amount has this check, withdraw and deposit, and as per my original code, right, I have check, withdraw, deposit. They're all within mutexes because I don't want different kind of race conditions. Code is very simple, and let's just run this code, okay? So I go here, where am I? Workspace, sorry. TLA plus, clear, okay. So I run this, I go to this my folder, and this is the code, and I have this program.cs, which is basically the boring part of the code. All it does is it just starts this class, right? It's a static class, this one, okay. So let's run this, okay? .NET run. So it'll take a few seconds to compile and run. I've used C#, but honestly speaking, you could use any programming language. But the weird part is that both of those transactions went through, right? It shouldn't have happened. So we have a problem here, but I don't understand what my problem is. And looking at the code, I mean, the algorithm is very simple, and I have implemented everything correctly. So if I look at the algorithm, I don't really see much of things that are wrong. All these operations are thread safe. And this is a small program, so just have trust in me. I've actually implemented this algorithm, and it seems to be correct, except it is not. So now I want to find out what is wrong with this code. So what I do is I write my code in TLA+. So this is my TLA+. Now this is +cal, and I'm going to transpile into TLA, and I'll show all the steps. But syntax I know is weird, but let's actually look at the code itself, right? So I have two people, Jack and Jill. I start with $100 in their account. I have this constraint, no overdrafts. This is basically an invariant. So at any point of time, there should not be any overdraft, which means the account balance should always be positive. And I am going to do two transactions simultaneously. So this process is called wire. So in TLA+, process is basically, think of it as thread in loose terms, right? There are some variables, and I'm going to test amounts, like I'm going to test this thoroughly. So test for all the amounts between 1 and as much amount the sender has, and make sure that everything works. So this is my process. These are my steps for that process. So simple. I have this amount, check the amount, then I have the withdraw step, and I have the deposit step. So sounds about simple. This is pretty much what I have implemented, and I'm going to run it. And I'm going to go down, and the first thing I have to do is pcal wire bug, okay? Sorry, pcal, not pcal. So +cal is going to transpile. It does kind of a little bit of weird stuff, but anyway, so it actually, when I look at it, it transpiles to TLA+, and TLA+ overwrites my file. Just implementation detail, you don't really have to worry about it. And this is my config. Config is the runtime thing that I am actually going to test. And what I'm testing is I want to test invariant. This invariant should hold true, no overdraft. This is the invariant I defined here, right? This is the invariant. I should not have negative balance. So now that I have, I'll see TLC, I'm using the command line tool, let's say wire bug. It says something weird happened here. So behavior up to the invariant, no overdraft is violated. This is what I observed experimentally, right? I observed that no overdraft was actually violated, and that's the reason why the negative balance fell. And now it's going to replicate and tell me what happened, why did this happen. So it says that, I'm going to run these two processes simultaneously. This is my initial state, so transfer, transfer, withdraw, transfer, and deposit, transfer, and deposit, deposit, and this is where something went wrong, that this is where the violation happened. And this is a race condition. So when I debug through this, and it actually, in this less than 1 second of execution, it actually examined 50 states. And these are some statistics and all those things, but basically this is where the bug is. So let's actually look at the code and see what happened. When you look at this algorithm, so let's actually look at this algorithm. What really happened was this bug happened when both of these threads enter video. So there were two threads that were executing this code. So thread 1 actually checked, everything was okay, right? Thread 2 also checked because I'm transferring $65 and $50. So these checks were done by both these threads, and both these threads entered here. So by the time the second thread, the first thread entered here, the second thread also had entered here, and hence this transaction was done simultaneously, which it should not have done. And that is the reason, that is the bug in this code. Now, couple of things I want to point out. This is a 4-line algorithm, and maybe if you are super smart, you might have figured this out, but I bet for very many of people, they could not notify that there was a bug here in 4 lines, right? If you can't find a bug in these 4 lines, do you really think you're going to find a bug in 1,000 lines of algorithm? This is the beauty of modeling. I can write an algorithm, I can model it, and without writing a single line of code, I am now able to find race conditions, deadlocks, live locks, you name it, I can do anything I want. And all I have to do is model my algorithm in a typical microservice. A model for me would basically be anywhere between 20 to 50 lines of code. That's all the implementation I have to do, and I can find a whole bunch of problems in my design. So let's actually fix it. So now, this is the fix. What I need to do is, as soon as I do the check, I do the withdrawal right there, because I don't want check and withdraw to be a separate step. So this is the fix for this algorithm, okay, which is check if this is true, and then just do the immediate withdrawal. So now I'm going to run the same thing here. I'm saying pcal wire fix, pcal wire fix, and then I just say TLC wire fix. I just want to make sure what I have implemented is correct, and sounds about, I don't see any error here. So it examined all the states and it said, well, what you did was correct, so that's good. Then I go back to my implementation, so I fix it. And what do I fix it? I basically have transfer where I do the check and withdrawal in one step, and if this succeeds, then I actually do the deposit step. So this is my code. I go back and I remove the buggy line, okay, that was where my bug was, and I just use the part where I fixed, and obviously, obviously when I now do did I save this file? I should save this file, just make sure I'm .NET run, it should work. What is it? Build failed because blah, 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 program which does not contain a definition for, oh, sorry, I actually made some funny changes in the morning, and I think I just didn't do that. Oh, this is the bug. Sorry about that. Okay, so I just renamed the function and didn't probably tested it. There you go. Problem fixed. Now, what happens with these kinds of problems is, obviously this is my whole premise is that if you have a difficulty finding bugs in this small code, how the hell are you expected to find bugs in thousands and thousands of lines of code? In real life, what happens is that these race conditions are very subtle and transient. So you write your code, you have your design, whether you write it in a piece of paper or not, doesn't really matter. You implement it, you run your unit test case, everything passes. You deploy your code in a staging environment, everything passes. You're going to run your code once, twice, maybe hundreds of times, thousands of times. and then you deploy it to production. Everything is great on day 1, day 2, day 3, and on day 4, something went wrong. There was an unusual race condition that only happens statistically when you run the code 1,000,000 times. Since you never tested, your unit tests don't test the code 1,000,000 times, or your staging environment didn't run 1,000,000 times, you actually never found that bug. And you found that bug in production 4 days after the code was deployed. That's how it happens in real life. And then you spend days, maybe weeks, fixing that bug until you realize that it wasn't so much of an implementation error as much as it is a design error, that there was something very wrong with the way you wrote that code in the first place. And guess what you have to do? For most parts, you have to have an extensive rewrite, or maybe 50%, 80% of your code to completely change your design, and that's going to be horrible, and that's something you don't want. So that's the whole premise of using the formal system, that I should be able to find these subtle bugs in my code using minimal amount of work even before I write a single line of code. Now here, I'll go past and I'll talk, every language has kind of various data types. So I'm trying to give like various language constructs of what TLA is. TLA plus itself is a relatively decently sized language, so I'm only going to be scratching the surface, right? I have values, strings, integers, booleans that I represent. Then obviously I have collections, tuples, we just saw the map, account one. I have various constructs, if then else loops that I would expect. And I have various operations that I have set operations and so on. So basically, I am using these constructs to write an algorithm. And the key thing that I have to do is that my algorithm, or my model as I call it, is a high-level model where I don't have to deal with mundane details like, implementation. So again, I have various invariants, assumes, assertions, checking, etc., etc. I'm just running past because I think I don't want to give too much details. This is all pretty well documented. I have labels and processes, awaits, so on. So tips for handling large models, right? TLA plus can have, so domain, reduce the domain, order steps in multiple processes, these can have state save, so create your abstractions, skillfully break your models into small parts, and there's something called symmetry sets. Like if I have a set and if there's an error in 2 elements, then there's probably an error in all elements. So you can use these symmetry steps. Now this is the interesting part. Amazon Web Services actually used TLA plus, and they still continue to use it to model their system. And this is the document you can find on Amazon publications, and this is basically an extract that I have here. That in one line, it's really helpful, right? And Microsoft uses TLA plus for Cosmos DB. That's the implementation they have. MongoDB uses it for fixing bugs. There's a Linux Foundation basically announced recently, this is fairly recent, TLA plus Foundation. Oracle was one of the founding members, so they have these announcements. So it just kind of tells you the practical utility of TLA plus. It's no longer a theoretical stuff, it's actually being used in the industry right now by big players as we talk. So coming towards the end, the summary, testing the design is important. We saw why. Right? Formal methods can be used. I just showed TLA plus, but the same thing is true for a lot of other formal methods, depending your preferences. They can be used to model system behavior. We saw in the demo how we automatically verified. Lets you detect conditions. Specifically for distributed systems, these are very hard to detect conditions. Okay, and I have some references towards the end. So if you want to explore, Leslie Lamport wrote this original book. This is a new book by TLA Plus, on TLA Plus by Hillel, and you have these websites, video courses. I mean, these are some of the links that I basically curated, but honestly, if you Google TLA Plus or any other formal method, you'll have a whole bunch of links. So in these days, knowledge, it's usually the time that is a constraint, not the amount of knowledge. With that, I would stop and I'm open to questions. Right on time.